example because you have to use de Moivre's theorem as a result of the powers, and you have to be able to turn Cartesian form complex numbers into polar form. So we need to remember a few things. First of all is I'd write down what de Moivre's theorem is. Oops, find my pen. So de Moivre's theorem, which states that if you have a complex number of the form r cis theta to the power of n, that it's r to the power of n cis n theta. The other thing that you need to remember is if you have a complex number of the form z equals a plus bi, we need to find the angle theta, which is arctan of the imaginary part over the real part, okay? And we need to find what modulus z is, which we call r, which is the square root of a squared plus b squared. So they're all the formulas you want to have rattling around in your head when you're doing complex numbers. So we have to work through this one now. We're going to look at the first complex number. We've got 1 plus I. What we need to do here is put everything in cis form first. Oops, I should say put in cis form. Okay, so that we can work with it. So 1 plus I, that's a nice one actually, because if you think about that as a picture, you've got that equal distance 1 in both directions. So we know that the angle theta is pi on 4, and we know that r is the square root of the real part squared plus the imaginary part squared, which is root 2. So 1 plus I equals root 2 cis the angle pi on 4. Otherwise, a good idea, just put a box around it so you can find that. Dealing with the next complex number, we've got 1 minus root 3i. Okay, this one we're going to need to use our formulas a bit more for. So first of all, I'll find what r is, the square root of the real part plus the imaginary part squared, which is equal to the square root of 1 plus 3, which is square root of 4, which is 2. So r is 2. For the angle theta, we need the inverse tan of the imaginary part over the real part. And just drawing a quick picture, this is 1 across, but root 3 down. So it's going to be a negative angle for tan. And if we think about our standard triangles, if we're dealing with tan and we're getting the root 3 on the top, the only way you can do that is using this angle here, opposite over adjacent, would get you root 3 on the top. So this is going to be negative pi on 3 because of where what quadrant it's in. So that tells us that 1 minus root 3i is equal to 2 cis negative pi on 3. And I'll put a box around that too. So we've got our two complex numbers now in cis form. So that means that we can now simplify this work. We can use de Moivre's theorem. So instead of writing our number like this, we're now going to write it in the cis form. So root 2 cis pi on 4, all of that to the power of 3, over 1 minus root 3i, written in cis form, which is 2 cis negative pi on 3, and that's all to the power of 5. Should put brackets around there. Okay, so we're going to use de Moivre's theorem now, so using this theorem. So what we know is that this is now root 2, all cubed, cis, 3 times the angle, so 3 times pi on 4, so that's 3 pi on 4, over, now we do the modulus to the power, which is 5, cis, and this time we multiply the angle by 5, so it's 5 pi on 3. Okay. With this one, I'll just do the working over here so you can see. Root 2 to the power of 3 is actually root 2 times root 2 times root 2. Root 2 times root 2 is 2. So the answer would be 2 root 2. Okay, so you've now got 2 root 2, cis 3 pi on 4, over. Now what you could do here is you could actually do figure out what that is, or you could simplify first if you wanted to. I'm going to just actually write down what that is, which is 32. We can do a bit of simplifying now. So we could cancel down both of these. So divide this one by 2, which is going to give you 16. Okay, so that just makes life a little bit easier. And now we can use our rule for division. So remember that our division rule, and I'll write this one down, is that if you've got two complex numbers, which are z1 over z2, then what you do is you take the two moduluses, r1, and you divide by r2. Cis you take the top complex numbers angle, theta 1, and you subtract the bottom one. So we're going to now work with this. I'll do this on the next page. Oops. Let's take that over there. Alright, cool. So let's work with this now. So we've got this cancelled down, so we've got root 2 over 16. Cis, the first angle, 3 pi over 4. Take away the second angle, which is negative 5 pi on 3. Now there's nothing much you can do with this. This is just how it's going to be. Root 2 on 16 can't be simplified. We can put all this over a common denominator, over 12, so times the top and the bottom by 3. And this becomes an add now, 2 negatives, times the top and the bottom by 4. So what we're going to find is we end up with root 2 on 16, cis of 29 pi on 12. And because that's really quite an ugly answer to have, I want to think about where that is in terms of the unit circle. We know that 2 pi is 24 pi on 12, so this is about here, 5 pi on 12 more, because it's 24 plus 5 pi. And, you know, I can write that so you can see that. 24 pi on 12, that's 2 pi, plus 5 pi on 12. So this is 2 pi. So all we're left with is root 2 on 16 cis of 5 pi on 12. And because this is a non-standard angle, there's actually nothing much that we can do with that. We have to leave it in that form. We can't put it into a Cartesian form. If you do have a standard angle, it's good practice to put it into Cartesian form. So that's the answer to that problem, which we had, which was 2 Cartesian form complex numbers to powers. Put them into cis form first. Use de Moivre's theorem after you've put them into cis form to cancel or simplify things down. Get rid of the powers so that they become multiples in the angles. And then use your division formula to finish it off to get your final answer.